First of all, go and put the kettle on. The maths of the ideal gas is very involved and you need to be concentrating and taking notes as we go along. Pause this, make a brew and come back. Imagine a cube with a P inside. That P is one particle of the ideal gas. We will build our maths around this P and how it travels around the box. This box is a cube, so it has a length L. That's it. The width is L, the height is L, the length is L, the volume is L cubed, the area of one side is L squared, the area of the outside of the entire box is 6L squared. Only one measurement for the box, L. The P inside the box is actually a particle. It is neutral. It does not have any type of charge, so is neither attracted to nor repelled, or vice versa, by anything else, be it the box or another particle. The P is also elastic. It does not change shape or deform. Momentum is conserved in collisions with this P. Kinetic energy is also conserved in these collisions. The P can wander around the box at random. It is one of many, many P's within this box. All of these P's follow the same principles as the first P, except their direction and speed are slightly different. Not much, but a little. The velocities of these P's form a distribution, and that will become significant later. For now, we go back to focusing on the individual P. It takes this P twice the length of the box divided by the velocity of the P amount of time for the P to go from one point in the box back to the exact same place. This is because velocity equals displacement divided by time. So time equals displacement divided by velocity. We have assumed that the P is only travelling in one plane of direction, let's say horizontally. That means the distance the P travels to go from one point back to the same point in one plane is equal to, it goes forward a length and back a length of the box, 2L. If we know how long it takes for our particle to go from one place in the box to the exact same place again, we might as well work out how often it does it. Frequency is the inverse of length of time, so frequency equals 1 over t, or 1 over 2L over velocity in the x direction. To put it another way, that's velocity in the x direction divided by twice the length of our box. Why have we bothered to work out frequency? Well, frequency is 1 over time. Force is change in momentum over time. So it can also be change in momentum times frequency. It is nice to mix things up every now and again. We have half of our equation for force in a particle in the x direction. We just need the other half now. What is the change in momentum of our particle when it hits a wall of our container? This bit's easy. We've done it in another podcast. Momentum is mass times velocity. In this case, velocity in the x direction. The change in momentum is the final momentum of our situation minus the initial momentum of our situation. P final minus P initial. As the mass of our gas particle doesn't change, then we need only give the change in the velocity of our gas particle. The speed doesn't change, but the direction reverses, so the initial momentum is plus P, and the final momentum is minus P. Minus P subtract plus P gives us minus 2P. If we talk about momentum of the wall instead, or we just change the signs around, we have change in momentum being equal to twice the mass times the velocity of the gas particle in the x direction. So now we have change in momentum and frequency. So we have force. Force of the particle on the wall equals twice the mass of the particle times the velocity in the x direction times the velocity in the x direction divided by twice the length of the container. Simplify that equation and we get an equation for force of a gas particle on the wall of the container in the x direction equal to the mass of the particle times the velocity of the particle in the x direction squared divided by the length of the container. That's force. So what about pressure? Pressure is force over area. In our box, we have to be much more precise than that. Pressure on the wall of the container from a gas particle travelling in the x direction is equal to the force of the particle in the x direction divided by the area of the wall in that x direction. The area is easy. Because the box is a cube, the area is L squared. But that is getting ahead of ourselves, so we will simply leave the area as A and see if we need to do anything about it later. Force in the x direction was worked out above, So pressure is this force divided by the area. Pressure in the x direction equals one of our molecules at the wall equals the mass of the particle times the velocity of this particle in the x direction squared, divided by the length of the container. All of this divided by the area of the wall we are hitting with our particle. In other words, mass of the gas particle times the velocity of the particle in the x direction squared, divided by a combination of the length of the box and the area of the box. Area of box times length of the box is volume of the box. So the pressure on a wall of the box is equal to the mass of a single gas particle times the velocity of this particle in the direction of the wall squared, divided by the volume of the box. We have a choice now. Do we go for volume or mass? Do we adjust this equation to go into all three directions, or do we adjust the equation to take into account the cumulative effect of all the gas particles in our gas cloud? All we have to do to make this equation apply to all three directions is divide by 3. So we'll do this slightly more complicated. We'll multiply the particles first, and we'll work out the equations for that.